Okay, in the boxes, okay, answer the following questions about nitrogen, hydrogen, and ammonia. In the boxes below, draw the Lewis electron dot structure, dot diagrams, I guess. Okay, you guys are getting pretty good at this, so let's start with nitrogen. I'd go N, and this guy has 2, it wants 8. This guy has 2, it wants 8. 2, 4, 6, 8, 10, 12, 14. ORP is 14. VE is 5 plus 5, or 10. ORP is bigger, greater than VE, or VE is smaller than ORP. When you don't have enough valence electrons, they do extra sharing. And this is actually going to do 2 extra lines, because the first extra line brings it down to 12, and the next extra line brings it down to 10. And so 2, 4, 6, 8, 2, 4, 6, 8. They both have 8, 2, 4, 6, 8, 10. Ding, ding, ding. That's nitrogen. Ammonia is a little um, easier. However, this molecule has hydrogen, beryllium, or boron in it. Remember Habib, or these have underfilled octets. So hydrogen wants 2, beryllium wants 4, boron wants 6, every other element wants 8. Hydrogen has 2, we don't add any. Hydrogen has 2, we don't add any. Hydrogen has 2, we don't add any. Nitrogen has 2, 4, 6, we have to add 2. And when I count, ORP is 2, 4, 6, 8. So valence electrons is 8. Sorry, ORP is 8. Valence electrons is 5 plus 1 plus 1 plus 1, which is also 8. So this is a sketch. This is a sketch. They didn't ask about shape. They didn't ask about polarity, nothing. So just move on. Calculate the standard free energy change that occurs when 12 grams of hydrogen react with excess nitrogen, according to the reaction below. So basically, the question, this is a Stoich problem. Now they've changed this notation. Remember, the new notation is it will be 34 kilojoules per mole Rxn. So what that means is if you have 1 mole of this, or 28.02 grams, and 3 moles of this, or 3 times 2.016 grams, you will make 2 moles of this, or 2 times 17.03, which I think is 34.06, something like this. It will release, because it's negative, 34 kilojoules. So the question is, if you have 12 grams of this, what will this be? And so this is a Stoich problem, and most important concept in all of chemistry is the mole. So what does 1 mole of hydrogen weigh? Well, it's 1.008 times 2, which is 2.016. So this is 2.016 grams per mole. And then here's my U flow. This is step 1. This is step 2. Step 3 is going to be the 3 to 1 mole ratio. And then this is step 4. Actually, this is step 4. And so I go 12 grams of hydrogen. If it bugs you that this isn't a ratio or a fraction, put a 1 there. And then there's 2.016 grams of hydrogen in 1 mole of hydrogen. And then the reaction shows a 3 in front of the hydrogen. And then per 1 mole Rxn. And then we can see that it's negative 34 kilojoules per mole Rxn. And interesting, I do this on the calculator, you get 67.4 something. This has 3 sig figs, this has 4, the counting 2, and so I have negative 67 kilojoules here. If you look at the scoring guidelines, it will say 68, but they use 2.0 here. Different sig fig rule, I don't know why, but because the rule is when you add, you count decimal places. My answer is right. Okay, now remember there's 2 delta H formulas. The one they want you to use is delta H is the sum of the bonds broken. That's called bond dissociation energy because the bonds break and the atoms dissociate. And the bonds that are broken are in the reactants. And what's interesting about this problem is they start out by letting you know that these are the bonds that are broken, this triple bond, and then 9 of these, because each one has 3 bonds, but there's a 3 in front of the hydrogen. And so it's the sum of the bonds broken, which are in the reactants, minus the sum of the bonds formed. And by this point in the course, we've already done the formula where you use the heat of the formation, or where you use the chart, the tables in the back of the book, where you use how much energy does it take to make a compound, which is logically equivalent to this. But when they ask about bond dissociation, you have to use a formula with bonds in it. And the reason why this problem is easy is they tell you the answer is negative 92.2 kilojoules per mole. Now, they don't have the mole RxN in because this is 2009, and they just started this new notation in 2013. And so, or 2014, one of those dates. No, 13, but the first test was in 14. But here's the deal. If the answer is negative, this has to be bigger. It's the only way it can happen. This, when you bonds, bond energy is always positive. So, so what has to be bigger? Well, the answer is, and I'll just write it out so that it's very clear. The bond dissociation of the products must be larger than the bond dissociation, energy, because it's in kilojoules, must be larger than the bond dissociation energy of the reactants, or the answer would not be negative. Something like that. Just use your math skills. Ooh. Good spelling on the word negative. All right. Next part. This is probably the trickiest problem on here. Oh, no, not this one. E is. Okay, why does it not surprise you? Let's go back to B. So we get N2 gas plus 3H2 gas goes to 2NH3 gas. Well, why is it not surprising that delta S is negative? Because you have 4 moles of a gas turning into 2 moles of a gas. And so the system is getting less disordered, which is logically equivalent to more ordered. But the reason we say disordered is because entropy is defined as disorder. So less disordered means that delta S would be negative. Okay, this one. Explain why there's a temperature. So before I begin anything, they told you in part B that delta G was negative 34 kilojoules per mole RxN. And they told you in part C that delta H was negative 92.2 kilojoules per mole RxN. And they told you in part D that delta S was negative 199, I think. I flipped the paper over. negative 199 joules per mole K. And so the question is, why is there a temperature above 298 at which this changes? Well, this is what I'd like to show you, that in order from delta G to go from negative to positive, this is calc, it first has to go through 0. And so where does it, now remember, if delta G is negative, we say it's spontaneous or thermodynamically favored. And when this is, because the reason why negative is spontaneous is when this system does work, that means it has the ability to do work, or work can leave. And then this is non-spontaneous. And in order to go from spontaneous to non-spontaneous, again, remember the new notation is thermodynamically favored, thermodynamically unfavored. In order to go from negative to positive, it first has to go through 0. So let's figure out if there is a temperature. Because interesting things happen if it's true all the time. When you try to solve an equation, you'll get an identity like 2 equals 2. And if it's never true and you try to solve the equation, you'll get some kind of contradiction. And if there is a temperature at which it flips, you can solve for that temperature. So gators are hell without tartar sauce. We want to know the temperature at which, let's just solve this for temperature. So I'm going to bring this guy over here and this guy over here. And so you end up with T delta S equals delta H naught minus delta G naught. And then if you want to solve for T, you would divide both sides by delta S. But an interesting thing happens. So we're going to put in 92.2 kilojoules per mole Rxn. And we're going to subtract 0, which we can just ignore because delta G, we're trying to figure out the temperature at which it flips from negative to positive. And then I'm going to multiply by the reciprocal of delta S, which is negative 199 joules per mole K. And mole Rxn, the new notation. Interesting thing, though, kilojoules doesn't cancel with joules, so then I'm going to do this. Kilojoules is on the top. 1 kilojoule is 1,000 joules, and then this cancels this, and this cancels this, and the only thing that hasn't canceled is Kelvin. And if I put this into my calculator, by the way, this is not how they do it on the scoring guidelines. I personally think my way is better because if you solve for the temperature, you've shown that there is a temperature. And so when you do this, you will get 463 K. And this has 3 and this has 3. And which is, not that you care about this, at 190 degrees Celsius. So at 463 is where it flips from being spontaneous to non-spontaneous. Oops, I don't know why I hit that. So let me read the exact problem again. Explain why there is a temperature above 298 in which the algebraic sign of the value of G changes. Well, it changes, it's going to change, when it crosses at 0. And so you're showing that there is a temperature and it is 190. I think that's good enough. Okay, so now this one's kind of crazy because they didn't in part B tell you, write it like this, but this is a Le Chatelier's principle because actually this should have been written like this, and I'm going to check that when I'm done. Maybe it was and I typed it wrong, but I didn't think so. But here's the deal. Theoretically, the best yields of ammonia should be achieved at low temperature and high pressure. So here's the deal. First of all, they told you that delta H was negative 92.2 kilojoules per mole Rxn. And so in other words, it's negative, so it's exothermic. So heat is a product. You're producing heat. And so what happens is if you have low temperature, that means if you take this equation and you cool it, this is Le Chatelier's principle. When the system gets cooler, it doesn't like that it's cooler. It will try to counteract that stress by shifting to the warm side, which is to the right. And then equilibrium will reestablish. But in order to shift to the right, it makes more NH3. And that's why the best yields is the more ammonium you make, the best yields it is. The other thing, what happens if you have high pressure? Well, the gas laws say that if you have high pressure, you have, sorry, I shouldn't say high pressure. If you increase the pressure from standard atmospheric pressure, you actually decrease the volume. And the stress is there's more crowding. And in order to relieve the stress of more crowding, it would switch to the side that takes up less room, which is, this causes the equilibrium to shift. The equilibrium shifts right. I don't know why I wrote shifting up here. The equilibrium shifts right, and if it shifts right, you have more NH3. And both of those things, and this is called the Haber process, because this is a huge chemical produced in America because of anhydrous ammonia. Is used as a fertilizer in agriculture. And so this is one of the chemicals that is made the most in America. And it's made by, it's called the Haber process because this is the guy who developed it. And it is run at incredibly low temperatures because that forces more of this to be made and incredibly high pressure. Okay, we're done.